In the last video, we talked about the paint command you can call from BASIC on a TRS-80 color computer or Dragon. It fills any shape you give it, painting with the color you choose and staying inside a border color you choose. We went over the different parts of the algorithm, including the paint line routine, the work item stack, border scans, and overhang checks. Today we dive deep into the bowels of the paint code. Why does it use a stack, which unfairly reverses the order of the work items? Get a look behind the scenes at how I figured out how the algorithm works. What is the exact order of the exact steps that the algorithm runs through? Rather than glossing over some of the quirks of the algorithm to make it easier to understand, I will reveal all its ugly truths, and also some nifty tricks to reuse common code and manually manipulate the stack. Plus, details on a bug in the paint code I discovered while working on this video. I honestly don't know if anyone else is aware of it. A quick look behind the scenes at the staggering imagery custom produced for the previous video. How I got MAME to animate a real-time view of the contents of the stack as work items get pushed on and pulled off. And finally, a couple of items just for fun. Can we build a test case that would cause the original paint code to overflow its stack? And can we get multiple paints running simultaneously on the same screen? This video gets more technical than the last one, and it assumes that you're already familiar with all the different components of the paint algorithm. So I would highly recommend you watch that previous video first. Think of this like the DVD extras to that previous video. And who watches DVD extras before the movie? Not every section of this video will appeal to everybody, but they're mostly self-contained. So feel free to skip around using the chapter headings in the progress bar. To keep things light, during the title screen for each chapter, I'll play an audio clip that an 80s kid growing up in the US might have heard many times. How many will you recognize? In the previous video about the paint algorithm, we talked about how it uses a stack to keep track of all of the directions it needs to go, but hasn't had a chance to go yet. I described the stack as a totally unfair, first-come, last-served, horrendous customer service experience. Like you're at the DMV from hell, literally. This may leave you wondering, why use such a messed up ordering? Why not just visit those work items in the order that they were added? Well, the answer isn't that ordering never matters. For example, I talked about a much simpler approach, depth-first search, which also uses a stack. Depth-first search is great for finding all the pixels that can be reached, but what if you were looking to find shortest paths from a starting point to various destinations? Depth-first search will not do that. But if you simply replace the stack with a queue, which is a first-come, first-served data structure, then you are assured that the first time you visit a location, you have done so in the shortest possible way. This is breadth-first search. Another classic algorithm for finding shortest paths is A*. It's again derived from the same series of steps, but simply changing the data structure to a priority queue, which doesn't care at all what order items were added to it, but simply serves up the most promising item first. So long as it uses a heuristic that obeys a certain invariant, not only are you assured of finding shortest paths, but A* will typically find them in less time than breadth-first search. So ordering really does matter. Sometimes. As it turns out, a reachability algorithm like Paint can visit its work items in any order at all. So it really didn't need to use a stack. So why did it use a stack? Because order doesn't matter. If Paint could use any data structure at all, why not use a data structure that you get for free? The 6809, like most CPUs, already comes with a built-in stack. It has a register that points to the current location of the stack. It has operations to push values onto the stack and to pull them off of the stack. And indeed, that is exactly what the Paint algorithm uses to store and retrieve its work items. So why does it use a stack? 'Cause it's there.
Sit, Ubu, sit. Good dog.
In recent weeks, Microsoft has released the source code to some retro software, like its 6502 Basic Interpreter, and even Zork of all things. What about the Coco's Extended Color Basic? Well, in quieter news, a few years ago, a team of dedicated Dragon enthusiasts gained permission and access to old ROM printouts, which they scanned, organized, and shared in this incredible GitHub repository of the Dragon Basic ROM. This was the biggest chunk of my source material. I copied just the paint routine, which of course would not assemble on its own, as it referenced several subroutines and other labels from elsewhere in the ROM. To resolve those references, I used the Unraveled series, an amazing publication in and of itself. A complete disassembly of the Coco's Disk Extended Color Basic ROM, created without the benefit of any source code at all, just very smart and dedicated individuals who made sense out of the uncommented, unlabeled, cryptic machine code burned into the Coco's ROM. And they did this back in the 80s, before any of the modern tools that we have all come to take for granted today. For each of the unresolved references from the Dragon source, I matched them up with the labels from Unraveled, located their addresses as they lived in the Coco ROM, and added defines for them. Finally, it assembled. So to check my work, I compared the generated hex bytes from my assembly with the hex bytes from the actual Coco ROM. A perfect match! My next step was to make the paint routine more self-contained, so it would be easier to run. Rather than paint getting its parameters by calling into the basic interpreter to parse a text command, my version copied the parameters from a simple block of memory that would be populated by a basic calling program. Finally, I was ready to start exploring the code and adding my own comments. Parts that made no sense to me, I would place behind a switch so I could turn it on and off and see exactly what it was doing. I added animation code so I could visually see what was going on with border scans. I added keyboard controls so I could step through the algorithm as slowly as I wanted and to have it stop at various interesting points. I used the MAME debugger with source-level debugging to explore the entire algorithm and see how each line would affect the registers and memory locations. By the way, source-level debugging is not officially merged into MAME, but check the description for a link to my source debugging preview repo so you can try it yourself. And of course, I added code to visualize the modifications to the stack, which I'll go over in more detail later on in the video. As an aside, I assumed that the actual original source code would be better commented and easier to read than the Unraveled disassembly. But there were cases where Unraveled had deeper and clearer explanations than the original source. Unraveled even identified a bug in the paint source, which was never fixed. This just made me admire Unraveled all the more. Some attentive viewers, like Lorem Foxy, noticed that there were places I left out some details. For example, although I talked about paint line, border scans, and overhangs, I didn't lay out exactly what order everything happens in. And in this comment, they noticed that the order seems to be inconsistent. If we find an overhang, do we explore the nook before we go to the next work item, or do we explore the next work item before we look at the nook? Assuming you're all well versed now in the ideas, you're ready for the full algorithm. Recall that the most important subroutine of the paint command is paint line. Rather than going pixel by pixel, we do entire horizontal line segments at a time. And this is how it fits together. Starting from a particular coordinate, we run paint line as far left as we can go until we hit a border or the edge of a screen. We then immediately check for left side overhangs. If we discover the potential for one, we will add a work item in the opposite north-south direction as we're currently going. But we don't pull it off yet, because paint line isn't done yet. Now paint line goes as far to the right as it can before it hits a border or the edge of a screen. Next, we add the usual typical work item to do the next horizontal line segment in whichever current direction we're going. So for example, if we were going south, we're now going to add a work item to go to the next horizontal line segment just below where we're at. Now it's time to do the border scan. traverse past any border pixels to see if there's another opening that our previous line would have been able to paint into. And if we find any, now add work items for those in the same north-south direction as we're currently going. Finally, we check for right side overhangs. And if we discover the potential for that, we'll go ahead and add a work item to explore the overhang in the opposite north-south direction as we were going. There just so happens to be another question in the same comment, which we will get to later on in the video. This one had me really confused and made things quite difficult to understand. These are the comments in the original source, and they talk about the structure of each work item on the stack. At the tip of the stack is one byte that gives us the direction. The direction ends up getting stored here in pdirect, and the comments helpfully tell us a direction of 1 means we're going up the screen, and a direction of ff means we're going down the screen. Except that's not at all what it means. 1 means we're going down the screen, and ff means we're going up the screen. To make matters even more confusing, Unraveled, which independently interpreted the machine code, agrees that the up-down flag is at the very tip of the stack, and they also seem to believe that up is 1 and down is ff. Up is 1, and negating that gives us down for ff. But they're all liars. All of them are liars. When the direction flag is 1, we actually go down the screen, and when the direction flag is ff, we're actually going up the screen. All I can think is that up and down does not signify spatial directions, but merely whether the y-coordinate is going up or down. And recall, y-coordinates go up as we spatially go down, and y-coordinates go down as we spatially go up, because the Coco screen coordinates are the opposite of Cartesian coordinates. So what's going on here? Did this code originally work on computers where y-coordinates obeyed Cartesian ordering? Or do they really think of going up simply meaning the y goes up, not even thinking about what it means relative to the screen spatially? And somehow that is so obvious that the Unraveled authors completely agree. Oh my gosh! This is why in the video I avoided this terminology and simply said north and south. Here's a paint partially in progress, and here's the work item on the top of the stack. I've already discussed that this north is a terminology that I'm using, because what would actually be stored on the stack is a code that means down. But I've got another bombshell for you. 9771 is not stored on the stack either. These are both off by 1. The x-coordinate is always 1 less than where we're going to start. So actually 96 is what's stored. And the y-coordinate is actually the y-coordinate of the previous line before we applied the direction. So we're actually storing a 72 because we're about to go north and turn that into a 71. So now I'm going to lightly walk through the highest level of this algorithm to demonstrate all of the intricate comparisons that we do that seem asymmetric and unintuitive, and that easily could have led to a bunch of off by 1 errors. Here's the code where we pull an entry off of the stack. The pull actually happens right here. And this comment from the original source tells us which register has which value. The very first thing we do is we add 1 to x. Why? Why do we store x as being 1 less than what we really mean, forcing us to have to add 1 to it immediately? Not sure. Maybe it simplifies the pushing code? But in any case, I compensated for this in the visualization and in the information that I conveyed in the last video. Let's keep on going. We store the direction, and then we can do a conditional branch based on it. If it's negative, we're going to branch down to here. And if it's positive, we're going to fall through. And here you see when it's positive, we increase our y-coordinate. And here when it's negative, we decrease our y-coordinate. Thus showing that what's on the stack needs this adjustment before we can even begin the paint line. Now if we continue through, this is the half of paint line that goes left as far as it can go. And assuming we did anything, this is where we check for a left overhang. The D register will contain a value telling us how far to the left we were able to go, how many pixels. We compare it with 3, and if it's strictly less than 3, then we skip doing the left overhang work item. That means we only do an overhang work item on the left if we were able to move to the left 3 or more pixels. So when we're 3 or more pixels, we adjust the X coordinate and then add the opposite direction work item. Here we then scan to the right as far as we can go. Here we enter the typical work item in the same direction that we're going, just as a result of the paint line itself. And then it's time to do the border scan. We get our counts in order, and then we loop through the pixels as long as we're looking at a border pixel. And if we find an opening that we can paint into, we'll jump here and do a paint line to the right for that opening, adding a new entry for the next line for that, which brings us back up here so that we can continue the border scan until we get to the end. Once we do get to the end, we end up here where it's time to check for a right side overhang. This time we subtract 1 from D, and if D had been 1 or fewer, then we would skip the overhang check. But if D were 2 or greater, then we'll go ahead and enter the work item for the overhang. So here we see on the right side, we need at least 2 pixels that we painted for there to be an overhang, but on the left side, there needed to be 3 or greater pixels. So all this shows that even if you understand something at a high level, actually implementing it is another story entirely. Getting all the numbers just right and all the comparisons just right could take twice as much time as it took just to come up with the algorithm in the first place. If you're used to coding in a more structured programming language, programming in assembly can be more like the Wild West. There are no rules. You can jump anywhere at any time. So trying to factor out common code is not quite as straightforward in other languages. Let's start with a fairly straightforward example. When we encounter the potential for an overhang, we add an entry onto the stack in the opposite direction we're going. That results in us branching here to enter L. We save a portion of the work item here, negate the direction, so we're going to toggle between north and south, and then we do the rest of the code here by following through into entcon. However, if we're entering a work item in the same direction as we're going, for example as a result of a border scan or just the typical work item after each paint line, then we'll jump here to enter S, again push about half of the work item, and branch back up to that same exact block of code. So either way, if we're going same direction or opposite direction, we've set up the registers in such a way that by the time we enter here, we're ready to push the rest of the work item onto the stack. This is pretty typical stuff. To save space and also improve the maintainability of code, you want to factor out as much common code as you possibly can, and then you'll probably have 1, 2, possibly even 3 or 4 entry points that all eventually branch into the common block of code. But let's look at something that's a bit more complex. The paint line routine is a bunch of code that we share when we're painting to the left as far as we can go and when we're painting to the right as far as we can go. But that might seem a bit complicated because the common part of the code is a loop. And in this loop we have to go left if we're supposed to be painting left, and we have to go right if we're painting right. So how do you share a loop that sometimes has to go forward and sometimes has to go reverse? The way they did this is by using a function pointer. There are 2 routines in the ROM, xdec and xinc. This one will decrement the current x coordinate of the pixel we're looking at, and this one will increment the current x coordinate of the pixel we're looking at. The y register is 16 bits, so we can load the y register with the address of either the decrement or the increment subroutine, and then use that function pointer inside of the loop. Every time it comes time to update the x value, we jump to the subroutine that's pointed to by y. Here we're calling our function pointer, and it might increment the x-coordinate, it might decrement the x-coordinate. But the cool thing is that the rest of this code, the rest of this loop, can all be shared. Let's return back to enter L and enter S, which push a new work item onto the stack. How do we actually get to this code? As you might expect, we branch to it as a subroutine. So anytime we want to enter an opposite direction entry, we branch to subroutine and enter L. Whenever we want to add a work item in the same direction, we branch to subroutine and enter S. But there's a catch. These routines are pushing work items onto the stack. The stack is what is used to save the return address. So if we're polluting the stack with our work items, how will we know to be able to return back to the place from which we called the subroutine that polluted the stack? And that's where stack surgery is required. Let's take enter L as an example. Once we get here, the stack will contain the return address from which to return once we're done. We pull it off. It is rare to see a pull without a matching push, but the matching push was the branch subroutine that presumably led us here in the first place. So we've removed the return address from the stack, we stuck it into Y temporarily. Now we start adding the work item bytes. We have that push over there. We have that push over here. And then we push Y back on. So basically we've snuck in our work item and we moved the return address to the tip of the stack. This way, when it comes time to return, we will return to the proper place, that return address will disappear, and all we're left with is the work item that we added to the stack. But if you thought that was some crazy Wild West stuff, hold on to your hat. We can do far worse to the stack than that. This is my favorite chapter. We're going to be talking about stack pruning. This is where the algorithm will detect that there are useless work items on the stack, and it will remove them before it even explores them. To me, that already is super cool because the way it's implemented is very much like exception handling, which wouldn't even appear in mainstream languages for years later. But it gets even better because this optimization actually leads to a bug that still exists in the code, and I honestly don't know if anyone has even seen this before. So we're going to walk through some examples of how stack pruning works, and then we're going to walk through individual test cases that bring us closer and closer to the bug itself. See how quickly you can figure out what the bug is. What the bug is? What the bug is. See how quickly you can figure out what the bug is.
Plop, plop, fizz, oh, what a relief it is. Plop, plop.
We're going to start painting the inside of this dude. And when we get to a particular spot, we're just going to pause. So you see we've been going down and then we came back up to the top of the head and we're going to start going back down again. We're going to come down through the left part of that eye. And then we're going to realize as we go around the corner that there might be more to explore going back up. So we're going to start going back up. You see we have one more line left to go, and that's here at y-coordinate 19, so we're going to fill it in. And in the process of doing that, we're going to want to continue going north. So we're now here at y-coordinate 18 and x-coordinate 58, which is right about here. Now you and I can tell that's already filled in. There's no need to do it again, but of course the algorithm needs to do it. It has been told it must do it. It is on the work item stack. Now one of the things the algorithm does that I haven't talked about yet is before it begins a paint line, before it begins a particular horizontal line, it puts a little marker. It remembers where it is on the stack before the paint line started. So this marker is going to point right here at the next work item, 3431. We're not going to do anything with it yet. We're just going to keep track of it. So first it's going to paint as far left as it can go, and then it's going to check for a left side overhang. And since it's going to extend left further than the previous line, that means there is the potential for overhang, which means we add a separate work item in the opposite direction to check for that overhang later. And you'll notice the x-coordinate is now 55 because it extended further to the left, but it has to finish the paint line, which means it now needs to paint as far to the right as it can go. And immediately after doing that, it adds the typical work item to continue on going north. So it's going to be on the next line above, 17, and again we're going to start it at x-coordinate 55. And now that we've completed paint line all the way to the right, it's time to check for a right side overhang. And indeed we did extend further to the right than the previous line, so we're going to add another opposite direction work item to the stack. This one starting at x-coordinate 72, on the line just below at y-coordinate 19. And now here is where the magic happens. Now that we've gone through the entire paint line, the algorithm asks, did I do anything? Did I actually change the picture at all? Did I really paint anything? And it sees that throughout this whole thing, no pixel has changed color. That means it's fruitless to consider any of the work items that have been pushed onto the stack since this marker, since we had begun the paint line in the first place. So we do a prune. Everything above that marker is completely removed. And in this way, we don't have to re-explore anything that we've already explored, thus adding yet more and more and more work items that are all going to result in nothing. This saves stack space, this saves time, this is genius. Let's take a look at how it does this in the code. This is toward the very beginning of the paint loop, where we pull the next work item off of the stack. After the pull, we do this. We remember the position of the stack in this variable pointer stack. This is that arrow that you saw earlier. This is just a reminder where we were when we pulled that work item off. Then we go through all of our stuff. We do our paint left, paint right, border scan, overhang check, all the way down until we get to the bottom. Once we're at the bottom, we jump back up to the top of the loop, and then we ask a simple question. Did we actually change the world this time around? This is a global flag that gets changed anytime we draw a pixel. It takes note of the color of the pixel before and after the draw, and only if the color changes will this flag get set. And once it gets set, it stays set until we explicitly clear it, which we only do at the very beginning of the loop. So assuming it actually did change, we go ahead and go to pull the next work item off, which is down here. But if we didn't, this one simple unassuming instruction does the prune. We take that arrow that we stored in memory and we stick that back in the stack register. That forces the stack to go back down to where it was when we captured that snapshot before. Anything we'd pushed onto the stack, we won't be looking at it. It'll be as if it's not there because the very next thing we push is just going to overwrite it. So this effectively pops all that stuff off the stack without doing anything with them. It just skips those work items and destroys them. Okay, you now have everything you need to know to figure out what the bug is. Feel free to pause the video here to consider. All right, let's walk through and see exactly what the bug is. We're going to run paint on this figure starting right here in the upper left-hand corner. Our paint color is going to be blue, and the border color is going to be yellow. So what do you think will happen when we start painting here? If that's what you guessed, that is correct. Now let's make a quick change. Rather than a yellow line here, we're going to do a blue line. We're going to start painting blue here again, and once again our border color will be yellow. What should we expect to happen now? Since the paint color is not a border color, we're just going to plow right through it, and that is exactly what we're supposed to do. We stop at yellow, we'll stop at the edges of the screen, but we don't stop at blue. Okay, final example. Again, we're going to start here in the upper left, painting blue, border yellow. What should we get? Ooh, that's the bug. It's supposed to plow through blue. Why didn't it plow through blue? Once we get to this line, and we do this paint line, we realize, we had no effect on the world. We didn't change anything. So the work item that we had pushed on to go afterward, which would have gone south to the next line and then continued on down, was pruned off of the stack because it was deemed fruitless. If painting this line did nothing, then any work items spawned from that should do nothing as well, and we skip them. And the reason is the assumption built into this test. What we're trying to avoid is repainting entire sections of the diagram over and over again. If it's already the paint color, no sense redoing good work. But what if it was already the paint color to begin with? In the unlikely event that an entire line is completely in that paint color, without any openings or anything else, the assumption will be that we painted it as opposed to it already having existed that way in the first place. That's why this example easily plowed through the blue line. There was another part of that horizontal line that was left open, so it seemed like we did make some progress as we did that horizontal line. But in the case where it's blue all the way through from left to right, then we will have seen no change at all, and we just stopped dead in our tracks because we prune off the next work item that would have had us continue past it. For the last nifty assembly trick, let's take a look at this subroutine here. The purpose of this is to take a look at the current XY coordinate we're at and return whether or not it is the same as the border color. It needs to go through a bit of processing to extract the byte for the current XY coordinate and then the bits within that byte for the current XY coordinate. This last instruction is just a fancy way to clean up a temporary that was pushed onto the stack and return at the same time. So think of this just as the return statement. So this is the interesting part, at least to me. This is where we compare those bits corresponding to the pixel with the border color. We're doing a compare without any kind of conditional branch, so effectively this just sets some bits in the condition code register. In the main debugger, we can see what happens when we execute that compare. We're about to execute it now, and this is telling us what the condition code register bits are set to. We can expect the compare to affect the N, Z, V, and C bits. And based on those bits, that's going to tell us what a conditional branch will do. For this particular subroutine, probably Z is the most important bit. When Z is set, that means they're equal, and a branch on equal will actually be taken. If Z is not set, then it won't be equal, and a branch on equal will not be taken. So watch what happens when we run the comp A command respect to these flags. So Z happened to be set before, but now it's not, and in fact the carry flag gets set instead. And here we're done with the test border subroutine. And so the very next thing we can do is a conditional branch, because the very last thing this thing did was a compare. And in this case, Z is not set, so the branch on equal will not be taken, and will just fall through. The reason I'm pointing all of this out is because I tend to think of a subroutine that returns a value as returning that value in a register, like A, B, X, Y, U, or maybe through a memory location. And it just doesn't immediately occur to me that CC is a register as well. And by returning a value in here, you make a subroutine that's supposed to return basically a Boolean value a lot easier to call, because the calling code merely calls it and then does a conditional branch right after. I'm sure this is super typical for assembly language programmers, but since I've only been back in this game for about 2 years, this sort of thing is still kind of striking me as novel. So I thought I'd point it out. In the last video, I had some very rough 8-bit graphics to demonstrate what the DMV in the underworld might look like. And it showed people gliding in and then kind of falling down. And we could add a bunch of people at a time, falling down. And then as they were ready to have their turn, they could kind of float up and then eventually be served. I really can't draw it all, but I did my best. I used GIMP to draw out the background and to add in some of the graffiti and the signage. To get the flames to animate, I just drew flames 3 times. So here's like one version of them. Here's another version of them. And here's another version of them. And I drew 2 versions of the person. One is when they're upright, and one is when they're lying down. And I used some Java code to convert the pixels from the bitmap into the byte format expected by the Coco. I used a simple basic driver to load the background in twice. One would be the copy that we would be showing, and then one would be off screen. And then finally I loaded the machine language program and then ran it. The main loop is pretty small. I first check for a keyboard command. If the space is hit, then we'll push a new dude onto the stack. And if enter is hit, then we'll pull the top dude off the stack. To keep things from going too quickly, I run a countdown each time through the main loop, and if it's not time to do any animation, then I just branch back up and try again. Otherwise, in order to animate, I erase the dude, I draw the next frame of the flames, I update the state related to the current dude who's flying around, I draw the dude, and then I repeat the main loop. I cheaped out in a bunch of ways. This is a pretty rough and dirty program. It's not like a game that has to be all polished. And I figured if it looks crappy, that just adds to the charm. So for example, let's take a look at how we draw the flames. We have a variable that points to the current flames frame. This is the position on the screen where we're drawing the flames. And I just have a simple nested loop where I go through the rows and the columns and I do it word by word, 16 bits by 16 bits. No optimization, so this takes quite a while. And each Flames frame has a fair amount of data. So that's a lot of bytes to be pushing to the screen without any kind of optimization. Drawing the dude is even slower because one part I didn't cheap out on is I'm doing actual bitwise operations. This allows the dude to be painted directly on top of the background rather than having some kind of solid color rectangle background behind the dude wherever it goes. So for each byte, I grab the byte currently on the screen, I apply the mask to it, then whichever pixels weren't masked get filled in with the colors of the dude, and I store it back. The reason for all the flickering is I fully erase the dude first, and I'm not doing any kind of double buffering. You may recall that I have 2 copies of the background in memory, but that's just so I can use one of the copies as my reference for fully erasing the entire rectangle of the dude. So the erase dude subroutine looks a lot like the draw dude, except there's no bitwise arithmetic. I'm just copying all the bytes from the background back on top of the dude wherever it was just drawn. Doing it this way clearly leads to flicker, but again, that's all just part of the charm. Along with the rest of the code in this video, there is a link in the description where you can find a freely downloadable copy of the code. This way, you can enjoy my very suboptimal code and improve it for your brand new game about the DMV underworld. In order to animate the stack as the paint algorithm was executing, I used a Lua script with MAME. I have a couple other videos on how you can script MAME with Lua, so for more information, feel free to check them out, but I'll review the core ideas here. The command line I used to launch MAME includes this part here. I pass the path to a Lua script as part of the -script command line argument, and this is that script. This script needs to communicate with the running code in 2 ways. It needs to be able to share memory, so it can figure out what to display as part of the stack, but it also needs a trigger, something to tell the script that something has changed, such as a new work item was pushed onto the stack or pulled off. So I reserved some addresses in the CPU's address space that will be shared between the Lua script and the running code. The contents of the stack would be exchanged through these addresses, and these addresses act as triggers. Whenever the contents of these addresses change, that triggers the script to run some code. Here we are in assembly language for the instrumented version of the paint code, and it also needs to know the same addresses. So it repeats those definitions here, and then it's responsible for writing to them as things change. So for example, each time we pull a work item off of the stack, we tell Lua where the new end address of the stack is, and then we trigger the pull code. And similarly, whenever we push an item, which as you might recall results in us calling either enter L or enter S, both of which result in calling through this code in entcon, we push the remainder of the work item, and again, we inform Lua of the new tip of the stack, and then write to the push trigger this time. When the script first starts up, it establishes a few global variables. This points to the main CPU object that's exposed by MAME. This points to the memory space exposed by MAME. And this points to the screen device exposed by MAME. Also, as the script starts up, it connects the triggers to Lua functions. The first trigger is attached to a function that gets called when paint starts, and the other 2 are triggered when we either push or pull a work item from the stack. We also connect one function to be run every single frame. This does all of the drawing. On each trigger, we need places to store the new information. So we have globals that keep track of where the work item list starts and ends, a pointer to a structure for the current parameters that we're currently using, and we keep track of an array of all of the work items that are being pulled off of the stack. In reality, when you pull off a work item, you just immediately begin executing it. But in order to facilitate the animation, we keep a work item in play as it's traversing through the screen from the stack to the top. And since things can get pulled off so quickly, we might not have completed that journey before the next thing was pulled off. So you can sometimes have a whole list of things getting pulled off. I'm not going to go through all of the code, but just as an example, let's see what happens when we pull an item off of the list. We have shared memory that tells us where the tip of the stack is, so I read that address. We also have some shared memory that tells us where the current parameters are that we're executing, so we pull that off too. And then we construct a new entry to go into that animation list. We start that entry as animating up. We populate its contents with whatever those parameters are. We calculate the starting positions of where it should be drawn onto the screen. And then we add it to the end of the array. We then use that information as we are drawing onto the screen each frame. We first loop through all the items that haven't been pulled off of the stack yet so we can draw those. We advance the animation data one frame. So that might involve pulling an item up or pushing it to the right. We print the current parameters that are actually being executed at the top. And then we loop through all the elements of the animation array and draw each of those where they're supposed to be drawn on the screen. And just as a reminder, all of the code, including this Lua code, is available for download. Just check the link in the description. Several folks have wondered that although it was very easy for me to overflow the stack with my simple depth-first search algorithm, would it be possible to stress the stack so much with the original paint that it would overflow as well? My first thought that was, since the screen resolution is fairly low, maybe it would be really hard, if not impossible, to actually force the algorithm to push so much onto the stack. Given all of its optimizations, it would actually overflow it. So I tried one of your ideas, where we use the border color in this checkerboard pattern, and then we paint from the top, effectively only over the white, using a third color. And boom! Although the program forcibly terminated, we didn't actually crash the computer. OM stands for out of memory. It was actually aware of its surroundings enough to know that it ran out of memory rather than just start overflowing other memory. In fact, if I were to list the basic program, it still has everything there in memory. I could even run it again if I wanted to. And crash the stack again if I wanted to. The reason Paint is able to so gracefully deal with the situation is it has dedicated code that runs every time we push a new work item onto the stack. It calls this subroutine with this parameter to ask if we have enough space left on the stack. This subroutine then takes care of just aborting the program if there isn't enough space. This, by the way, is the bug that I mentioned earlier that Unraveled discovered, because this parameter that they're passing isn't big enough. It really should be 3 instead of 2. But in most cases, we can get by with just checking for 2, as you saw. And now here's something that no one asked for, but you're all getting anyway. What would happen if we could run 2 paints at the same time? For example, what if we could paint the inside of the spiral blue and the outside of it red simultaneously? What might that look like? Or what would happen if we ran 2 paints in the same region? What if we started painting blue on the inside of the spiral up here and red on the inside of the spiral from down here? Who would win? What if we could run more than 2 paints at a time? What if I turned this buff to cyan, this magenta to buff, this buff to cyan, and this magenta to buff, and then the whole inside of the ghost to orange? The eyes will finish pretty fast, so watch them when we first start. What if we did a competition? What if we just started with a blank screen, painted blue with a red border up here, a red with a green border over here, and then a green with a blue border down here? Kind of like a rock, paper, scissors game. Who would come out the victor? Well, looks like blue is completely getting supplanted by red, and green is going up to catch up to the red. Oh, some slits of blue are coming through, but red is now taken over, and green is taken over. Who is going to win? What a very exciting game. Red seems to be getting erased by that green now. Oh my gosh! Blue came out of nowhere! What happened with blue? It must have had a work item just waiting to catch up with everybody else. Unbelievable! What a turnaround! If you're curious how I got multiple paints to work at the same time, it was just a silly little project I did because I thought it would be cool. I'm not really planning to discuss it in detail, but let me know if you have any ideas of how you would do it. This one will decrement our current X pixel. To keep things light, this one will decrement the... To keep things light, I'll play an... what? This one will decrement the X coordinate. In the US might have heard many times. This one will... Golly. To keep things light, during the title screen for each chapter, I will play an audios clip. Audios clip? This one will decrement the current X coordinate of the pixel. Darn it, I almost had it that time. Mother...